Hello, and welcome to the lecture for the TI Precision Lab discussing instrumentation amplifier topologies, specifically 1-amp IAs. To recap, an IA can be idealized as an electrical circuit that amplifies the signals that differ between its inputs and rejects the signals that are the same on both inputs. This lecture will cover how this can be done with one op-amp and a few passive components. The simplest form of an IA is an op-amp with 4 resistors. This particular configuration is called a difference amplifier, which fulfills the primary behaviors of an idealized IA. You'll see that many of these pins are familiar from the IA pin diagram shown before. The function of this difference amplifier is to amplify the difference between the two inputs. The common goal of this configuration is to match R1 to R3 and R2 to R4 to yield a gain ratio of R2 over R1. Let us now derive the transfer function using superposition. To refresh on the method of superposition theorem, we will derive 3 equations, V1 star, V2 star, and ref star. In the first equation, we will derive V1 star by shorting V2 and ref to ground. In the second equation, we will derive V2 star by shorting V1 and ref to ground. And in the last equation, we will derive ref star by shorting V1 and V2 to ground. Lastly, we will combine these 3 equations to yield Vout. Let us assume that all resistances equal each other, meaning R1 is equal to R2, which is equal to R3 and R4. We will ground the non-inverting input V2 and the reference voltage ref to derive the corresponding output equation. This now looks like a unity gain inverter with a transfer function equal to Vout is equal to V1 multiplied by negative R2 over R1. Since we assumed all resistors are equal to each other, then the output equation becomes Vout is equal to negative V1. This is the gain looking into the inverting terminal. We will name this equation V1 star. Going back to our original configuration, we can see that the non-inverting input is connected to a voltage divider formed by R3 and R4. The voltage seen at V2' can be broken down by 2 current equations. I1 is the current flowing through R4 and is defined as V2' minus ref over R4. I2 is the current flowing through R3 and is defined as V2 minus V2' over R3. Since there is no path for current to take another loop, these currents must be the same. If we set these 2 equations equal to each other and solve for V2', we get V2' is equal to V2 plus ref divided by 2. We will use this equation in the next slide. Now, let us ground the inverting input V1 and the reference voltage ref and derive the corresponding output equation. We can recognize the circuit as a non-inverting amplifier, so Vout is equal to V2' multiplied by 1 plus R2 over R1. We previously calculated V2' to be equal to ref plus V2 divided by 2. Let's plug this in to V2' in the top equation. Since we assumed all resistors to be equal to each other and we grounded the reference voltage, the output equation becomes Vout is equal to V2. This is the gain looking into the non-inverting terminal. We will name this equation V2 star. Now, let us ground the inverting and non-inverting inputs, V1 and V2, to derive the output due to ref. Since all the resistors are equal to each other, ref and V2 are interchangeable. The circuit can be redrawn as such. This looks like the familiar non-inverting configuration with Vout equal to 1 plus R2 over R1 multiplied by V2', where V2' is half of the reference voltage since R3 is equal to R4. Our output equation Vout now becomes 1 plus R2 over R1 multiplied by half the reference voltage, which further reduces to Vout is equal to ref. We will name this equation ref star. Let us recap the equations we just derived. Equation V1 star is Vout is equal to negative V1. This has inverting gain to the output. Equation V2 star is Vout is equal to V2. This has non-inverting gain to the output. Equation ref star is Vout is equal to ref. This is the output due to an applied reference voltage. Let us use the superposition theorem to combine equations V1 star, V2 star, and ref star. Combining these 3 equations yields Vout is equal to V2 minus V1 plus ref. This topology yielded the difference between the two inputs, satisfying the first characteristic of an ideal IA. Let us now analyze its ability to reject the common mode signal. By definition, the common mode input voltage is equal at each input and splits the differential voltage as shown here. V1 is equal to VCM minus half the differential voltage, and V2 is equal to VCM plus half the differential voltage. Plugging this into our output equation and simplifying, we get Vout is equal to Vd plus ref, where Vd is equal to V2 minus V1. So it rejected the common mode voltage, leaving only the differential voltage. In our derivation, we assumed all resistors were equal to each other for simplicity. The general equation accounting for each unique resistor in the circuit is equal to the following equation. Let us now take a look at a more common use of this topology, where resistor matching is desired to yield a simpler output equation. In order to simplify the transfer function of this circuit, we can match R1 to R3 and R2 to R4. The general equation from the previous slide simplifies to Vout is equal to R2 over R1 multiplied by V2 minus V1 plus the reference voltage. V2 minus V1 is the differential input voltage Vd, and R2 over R1 is the differential gain of the circuit, Ad. This should look familiar to the general IA equation from previous lectures. Let us now take a deeper look at the differential gain, Ad. There are two types of gains which are associated with amplifiers, noise gain and signal gain. The signal gain of a circuit determines the input-output relationship. This is dependent on the amplifier's configuration and is defined as Ad for a difference amplifier. The noise gain of a circuit determines many features of the amplifier, including bandwidth and stability, and is defined as the non-inverting gain. In the case of our difference amplifier, noise gain is 1 plus Ad. See the examples on the right-hand side. The top circuit is a simple non-inverting configuration with the signal gain equal to 1 plus R2 over R1. The noise gain is the non-inverting gain, again 1 plus R2 over R1. The next circuit is a simple inverting configuration with a signal gain equal to negative R2 over R1. The noise gain is the non-inverting gain, so that is 1 plus R2 over R1. The last circuit is the 4-resistor difference amplifier with the signal gain Ad equal to R2 divided by R1. The noise gain for a difference amplifier is 1 plus Ad, or 1 plus R2 over R1. So even in unity gain, the bandwidth of a difference amplifier is cut in half. Back to our circuit, you can see that the gain of this circuit reduced to R2 over R1, which assumed perfect resistor matching of R1 to R3 and R2 to R4. Resistors cannot be perfectly matched in production, and series resistance may appear at the inputs, so the common mode rejection ratio, or CMRR, will be degraded. Let's take a look at an example of the effect of this mismatch. In production, resistors are labeled according to their tolerance ratings. A 1% 1 kiloohm resistor can be up to 10 ohm off and still be within tolerance. It's important to note that this tolerance does not include temperature drift of the resistor. Additional resistor error can be due to soldering joints and PCB traces. These errors may lead to significant CMRR degradation. Let's take an example where we have an amplifier with 4 1 kiloohm resistors with 1% tolerance. R1 and R4 varied in one direction to 1.01 kiloohm, and R2 and R3 varied in the opposite direction to 990 ohm. Ideally, we aim for R1 to match R3 and R2 to match R4 because the gain will be R2 over R1. However, R2 does not match R4 and R1 does not match R3. Common mode input voltage is equal at each input, so the expected output of this circuit of 0 volts becomes approximately 20 millivolts. This translates to 34 dB of common mode rejection. This table shows the potential worst-case CMRR for varying tolerance resistors at gains of 1, 10, and 0.1 volts per volt. The CMRR performance due to resistors is especially important for low-gain or attenuated circuits. A disadvantage of a difference amplifier is low input impedance. Before delving into this, let us first define how to measure the input impedance on an IA. Normally, one defines input impedance as a change of input voltage divided by the corresponding change in input current. Voltage feedback op-amps normally have both differential and common mode input impedances specified. RDiff is the differential input impedance in the image shown here. For a 4-resistor single amp IA, that is the sum of the two input resistors, or R1 plus R3. RCM plus and RCM minus are the common mode input impedances looking into each terminal individually. While there have been many various historical definitions across the industry for common mode input impedance of a difference amplifier, we define RCM here as the parallel combination of the inverting and non-inverting paths. That is what a signal common to both inputs would see, and is equal to R3 plus R4 in parallel with R1 plus R2. In the last slide, I mentioned that a difference amplifier's low input impedance can be a disadvantage. Why? Let's take a look at these 4 unity gain difference amp circuits. In the top left-hand circuit, we have a 1 kilo-ohm shunt resistor with a 1 milliamp source. We expect to sense 1 volt, but our output is 750 millivolts. In the top right-hand circuit, we have a 1 mega-ohm shunt resistor with a 1 microamp source. We expect to sense 1 volt, but our output again is 750 millivolts. In the bottom right-hand circuit, we again expect to see 1 volt at the output, but we measure 500 millivolts instead. In the bottom left-hand circuit, we have a 1 kilo-ohm shunt resistor with a 1 milliamp source. We expect and measure 1 volt at the output. These varying results are all due to the input impedance of the difference amplifier, as this will draw current from the signal source. The ratio of the source's output impedance to the difference amplifier's input impedance determines how detrimental this current draw is. Even if the current draw does not lead to huge inaccuracies, the input impedance of a difference amplifier loads the voltage source connected to it, which may drain a battery. When designing circuits, carefully choose your difference amplifier so that the overall system requirements can be met. We recommend that the input impedance of the difference amplifier be 100 times greater than the source's output impedance. In many cases, the source is pre-selected. This means you have no control over its output impedance. You may need to redesign your difference amplifier to accommodate this source. What if your source's output impedance is very high, like 1 megaohm? 100 times this would be a very large resistor. As we know, large resistors come with their own set of drawbacks, including higher noise. Let's take the example from the last slide. We have a 1 megaohm shunt resistor with a 1 microamp source. We expect to measure 1 volt, but our output is 750 millivolts. As we previously discovered, this is due to the input impedance of the difference amplifier. Let's take the case where you are stuck with this 1 megaohm shunt resistor. How can we alter the 4 resistors around the difference amplifier for high accuracy? We can use the equations for differential and common mode input impedance. RDiff is defined as the sum of the two input resistors. Ideally, this is dominated by R1 plus R3. However, in this example, the shunt resistor is large enough to make an impact on this value, specifically on the current draw through R1. Looking at the inverting input, the input impedance is R1 plus RS, which is equal to 2 megaohm. Looking at the non-inverting input, the input impedance is R3, which is equal to 1 megaohm. This level of mismatch leads to the imbalance of current draw from the source and thus error at the output. If we modify R3 to be 2 megaohm instead of 1 megaohm, and then adjust R2 and R4 to match this for unity gain, then the effective current draw is now matched and our output is as expected. You might be asking yourself, what if the resistors are integrated to the IC and you can't switch them out? In this instance, we can add one resistor to the circuit. Let us cover an example of this. Take this INA 592, TI's high-precision, low-power E-trim difference amplifier. The INA 592 features an integrated precision resistor network to achieve gains of 2 or 1/2, depending on how you connect the circuit. The connection shown here is for a gain of 1/2. In the circuit to the left, we have a 12 kilo-ohm shunt resistor with a 250 microamp current source. This generates a 3-volt differential. In a gain of 1/2, we expect to see 1.5 volts at the output, but we see 917 millivolts instead. Again, this is due to the input impedance of the difference amplifier. Since we cannot access the resistors internal to the device, we can improve accuracy by adding one resistor in series with R3. If we add a 12 kiloohm resistor in series with R3, RDiff- and RDiff+ match. You'll notice that the output is 750 millivolts. That's because by adding that resistor, we have changed the gain of the circuit to be 6 kiloohm over 24 kiloohm, or 1/4. It's important to note that the internal resistor network of this INA 592 is ratiometrically matched in order to achieve gains of 1/2 and 2. The absolute value of these internal resistors may vary up to 15% in either direction, depending on process. Keep this in mind when you are relying on absolute values to determine the fifth added resistor. Calibration would likely be required to achieve very high precision. In a future video, we will cover a 3-amp IA topology which resolves these input limitations. As simple as this 1-amp IA topology is, it does come with its own set of disadvantages. Beyond the fact that its precision heavily relies on matched resistors, this topology has low input impedance. This circuit will draw current from the signal source, and if the source's output impedance is not zero, it will degrade accuracy. That's not to say that a 1-amp IA should never be used though. They just require extra attention. If you have an application where you are processing low impedance sources and high common mode voltages, this 1-amp IA topology can be exactly what you need. Please continue to the next lecture where we will cover a few 1-amp IA use cases. That concludes our third video discussing the 1-amp IA topology. Please try the quiz to test your understanding of this video's content.